Hello students, in this video we'll see an example of how to compute a Fourier series of a complex exponential term. Let's consider the function f of x is e to the I pi alpha and then e to the minus I alpha x, where alpha is not an integer and x is in the interval 0 to 2 pi. Okay, so I'm looking at this periodic function over here. Okay, of course, if I shift x by 2 pi, well, we know that this is going to be a periodic function, right? And so what I would like to do is I want to find the Fourier coefficients in the Fourier series of this function. So let's find the Fourier series. So clearly, let's look at the first Fourier coefficient. Let's look at f hat of 0. So f hat of 0 is going to be 1 over 2 pi. I'm going to pull this constant factor out. That's just a factor that's going to allow my calculations to work a lot smoother. Negative pi to pi e to the minus I alpha x. Then what? And then just the 0 mode just gives me nothing here. I have a dx. And so this is going to be a 1 over 2 pi e to the I pi alpha. And then I'm going to have an e to the minus I alpha x over minus I alpha from x goes from 0 up to 2 pi. Okay? And so what we get over here, we're going to get that this is just going to be a e to the I pi alpha over 2 pi. And then I'm going to flip the limits of integration. Since there's a negative sign here, I'm going to just change these orders. So I'm going to plug in the 0 first. If I plug in the 0 first, we're going to get a 1 minus e to the negative I alpha times 2 pi over just I alpha. That's the 0 mode over here. Great. And so in general, we're going to see how this, the general formula over here is going to much be the same. Now, the one thing I want to notice over here is that what this is going to be an e to the I pi alpha minus e to the minus I alpha pi, because I just combine those exponents, over a 2 pi I alpha. The 2i and that is going to give me just a sine. So this is going to be a sine of alpha pi over, what's left over is just going to be a pi times alpha, Great, okay? So this factor is going to persist, so I'm going to have to, if I decide to rescale things, I've got a very nice formula using this idea over here. So I'm most likely at the end of the day going to rescale things by this factor because the formula is going to persist. So let's do the next calculation. So will f hat of n be? So f hat of n for n not equal to 0, n not equal to 0, implies what? Implies that f hat of n is 1 over 2 pi e to the I pi alpha, integral from, well, I put a negative pi to pi here. Let's change, so I really might, sometimes I'll flip into this. That should really be a what? That should be like a 0 to, I'm doing 0 to 2 pi. So force of habit over here. So 0 to 2 pi. It won't matter if I can shift these things, and the fact that by the periodicity it won't change anything, but to be completely formal about it, I'm using those limits. So I should put a 0 to 2 pi here. So 0 to 2 pi. And then what? And then e to the minus I alpha x, e to the minus I n x dx. Okay? And so now what will this give us? This is going to give us 1 over 2 pi e to the I pi alpha. And then I'm going to combine these exponents over here. So this is going to be a what? This is going to be an e to the negative I ix, and then n plus alpha over negative I n plus alpha, and x goes between 0 and 2 pi over here. Great. And so what we're going to have, so again, I'm going to flip the limits of integration like so. And so we're going to get a 1 over, I'm going to have an e to the I pi alpha over 2 pi. And then what? And then a 1 minus e to the negative 2 pi I n plus alpha over a total of n plus alpha, because I flipped the negative sign. Great. And now the important thing to realize here is that e to the 2 pi I n is, since n is an integer, I can just discard this term because that's going to give me a 1 by the periodicity. So I can just, that will turn into a 1 by the periodicity. Okay, and so then what we're reduced with is I'm going to factor that through. So this is going to be an e to the negative 2 pi I alpha. I'll do the same trick as before. So this is going to be equal to what? This is going to be equal to a 1 over 2 pi. And then I need an I in the denominator over here as well. So we need an I, and then n plus alpha. And then what goes on top? What goes on top is just going to be e to the I pi alpha minus e to the minus I pi alpha. And now again, I can use the fact that I'm going to see this sine term over here. So this is exactly just going to be the sine of pi alpha over, that gets rid of the 2 and the I, over pi times n plus alpha. And so we see we can actually combine these two expressions over here. So for any n, we can conclude this. For any n, f hat of n is equal to the sine of pi alpha over pi times n plus alpha. And this formula clearly works when n's equal to 0. I will definitely get this when n's equal to 0. So this is the general formula over here. And so what have we just proven? We've just proven that e to the I pi alpha, e to the negative I alpha x is equal to the sum over n and z, like that, of these numbers over here, sine of pi alpha over what? Over pi n plus alpha squared, e to the I, there's no squared there, there's just a regular coefficient over here, like that, e to the I n x. Okay, those are our Fourier coefficients. And now in particular what I can do is I can use Plancherel's theorem, because this thing is unimodular over here. This is e to the I something, so this thing is unimodular, so the L2 norm of this function over here, so the L2 norm of this thing over here is just going to be 1, e to the I pi alpha, e to the minus I alpha x. The L2 norm of this thing squared is just going to be 1 since it's unimodular, since it's e to the I something. And so by Plancherel's theorem, or Parseval's theorem, either one, what can we conclude? We can conclude that 1, so by Plancherel or Parseval, we can conclude that 1 is equal to the sum over n and z of what? Of the sine squared of pi alpha over pi squared times 1 over n plus alpha quantity squared. And so in particular, I can do this is a constant. This does not depend on n. So we can conclude from this, we can conclude that the sum over n and z of 1 over n plus alpha squared is equal to pi squared over the sine squared of pi alpha for alpha not an integer. So in other words, what we have over here is we can recognize this as actually just what? Is pi squared, and 1 over sine is cosecant, so this is going to be cosecant squared of pi alpha. So I have an infinite series representation for cosecant squared of pi alpha, where alpha is not an integer, and this formula over here allows me to compute a wide variety of different number theoretic properties of these reciprocals of the sum of the squares. Thank you very much.